Yes, hi. This is George Larakis again, and today I would like to talk about Math 209 from Concordia University here in Montreal, Canada. And I will be talking about differential equations, growth and decay. So first of all, what is a differential equation? I mean, differential equation is anything that involves the function y in an equation where it's also present derivatives of this function. What do I mean by that? Let's say, for example, y plus y plus y is equal to 0. So the second derivative plus the first derivative plus the function itself equal to 0. So this is a differential equation. And yeah, I mean, what will be, I mean, today we'll just scratch the surface of this, because this differential equation, it's a whole course by itself. So, but here we'll just scratch the surface, and I mean, we'll only be working with equations that they have only the first derivative. So, I mean, something like that, and this is called first order differential equation. Okay, so I mean, let's now see how we can solve a differential equation. So, as I said again, let's say we can rewrite what I just wrote before as d. So many pens and nothing is writing. Okay, so dy over dx is equal with f of x y. So that's basically the differential equation that we'll be working today. How we'll solve this equation here? It's, I mean, here you see that you have x and y. So let's say that this here, you can break it in a part where you have, let's say, a g of x and h of y. Okay, this thing here, it can be written in something of this form, like, which includes two equations, two let's say smaller functions, that the one is a function of x and the other is a function of y, and that's the only case that we will be studying today. So in this case, what you should do is you should try to bring the part with the y here, so that will make it h of y dy, that's equal with g of x dx. And of course, now if you take, what we do, the next step is you take the integral of these of both sides, here with respect to y and here with respect to x. And from there it's very simple. Just y, it will be, I mean, here you will have a function of y, which will be the integral of this, which again, you don't have to worry because it's, we're just dealing with very simple cases. So let's say here you will get a function capital H of y, and here you will get a function, let's say, capital G of x, and of course you add the c here, and that's the solution to That's the solution to this differential equation. And this is called the general solution. And in some problems where they give you some initial conditions or some other condition of the problem, you can go and substitute it and find this value C. And when you replace this by the value of C, you will have what we call a particular solution of differential equation. But because all this might sound boring, but again, this is important to know your theory. So let's do an example. Okay, so let me get an example here. And these are very simple examples. Okay. Okay, for example, because this is also, let me do something else first. Yeah, let's do this here, which is problem 11 of the book that you use at Concordia University. I mean, they might differ a little bit because the book I have, it's an older edition. But in general, is the same. So, okay, so we have to find the general and particular solution for the following cases. So the first one is to find if you have this differential equation here, dy over dx is equal with 7 over x. To find the general solution, I mean, this is really very simple. I mean, what I said is you try to take the x with the x and, the y with the y here. Of course, we don't even have any y. So what you should do here is you should just keep the dy here. And here you should just have 7 over x and bring here the dx. And now just find the integral of these two things. And of course, the integral of dy is y. And the integral of 7, the 7 you take it outside of the integral. And the integral of 1 over x is ln x. And of course, here you put plus c. And that's the integral, that's the solution to this differential equation. It's really a pretty simple case. So now let's do the next one. Okay, so the next one, which is, let's say, a step further, it's the following. It's number 15 of the same book. So here what we have that dy over dx is equal with x squared minus x. And here we have also the condition that the y at 0 is equal to 0. So, and here we're looking to find the particular solution. Again, this is simple because, I mean, all of them are simple, but this is very simple again because we don't even have a y somewhere here. So, so what we do is we keep the dy to the left and we bring the dx to the right. So, and now you take the integral in both sides, and that's about it. So the integral of dy is y, and the integral of this here, it's the x squared is x to the third over 3. And the integral of x is x squared over 2, and of course you add the c. And now, so this is the general solution, and now you want to find the particular solution. I mean, before we go and do that, let's make, I mean, because this is also part of what we will be doing, it's if you have a function, to check if this function is a solution of a differential equation. I mean, and how we do that, it's you take, for example, this here, we find that is the solution of this differential equation. So if we want to confirm that, which is very easy, what you have to do is you have now to take the derivative of this and prove that it's equal with this. So indeed, if you take the derivative now of y prime, that should be 3x squared over 3 minus, sorry, here we missed 2, minus 2x over 2 plus the derivative of a constant, which is 0. So, of course, if you cross out, you see, of course, that as expected, this here, it's equal with this. So that means that, the answer is correct. So, and we said that this here is the general solution. Now, if you want to find the particular solution, it's nothing complicated. You just have to take the conditions that we have here. So, and apply them and find the c. So if you put whatever x0 and y0, what we'll get here, we'll get that 0 is equal, all these will become 0, and this is 0, so it's equal with c. So that means that c is equal with 0, so that means that the particular solution, it's y is equal with x to the third over 3 minus x squared over 2. And that's about it. So, now, let's see how this topic here is related with this course, which is actually somehow applications on commerce, business, and social science. So, I mean, let me tell you something. Okay, so if you have a differential equation of the form dy over dt is equal with ky, okay, where you have that k and t, they are greater than 0, and y at 0 is equal with c. So, I mean, if you just solve this if you solve this differential equation, I mean, here for the first time you see that you have the y. So, I mean, what we will do, since we have y here and we have the dy here, so you have to bring this down here, so it will be with the y. So you have dy over y. The k, you leave it here, you bring it down, doesn't matter because it's a constant. So let's keep it here. So dt. So, and now what we have, again, now you take integral in both sides. And the integral of this here is ln y. And, of course, the integral of this is k t, and of course, plus c. And now, like if you apply the initial condition, we will have that for t is equal with 0, t is equal with 0, the y is equal with c, so that means that ln c is equal with c, so that means that ln c is equal with c. So ln c is equal with c, okay. That means that c is equal Just give me a second. Okay, so before we go there, here we have that ln y is equal with this. So according with the definition of the logarithmic function, that means that y is equal with e to the kt plus c. And this we can write it as y is equal with e to the kt times e to the c. So, and now, of course, if you, in this equation here, if you substitute that t is equal with 0, you have that the y is equal with c. That should be equal with e to, all of these will become 0, so e to the 0, which is 1, so this here should be equal with e to the c. So now if you go and you substitute back the here e to the c equal with c, you have that your equation becomes c e to the k t. Okay, and now the graph of this equation, here. Is symbol, it's the exponential function, which goes like this. And of course, here we said that at t is equal with 0, so here you have t and here you have the y. So we said that t is equal with 0, the y is c, so that means that this point here, it's 0 point c. And this has to do with growth, okay, because the y is increasing exponentially with time. And in the case that, in the case that you have a minus here, this is, if you solve this problem again, you will get that the solution now, it should be if you solve this, it's exactly the same. You will get that the solution to this differential equation, it will be y is equal with c e to the minus kt, which if you want to graph it, it's something like this. And of course, here is t, and here is y, and of course, this here is c. Because again, at t is equal with 0, the y is equal with c. And of course, this is a decay because the y is decreasing exponentially with time. That's, I believe, pretty simple stuff. And now, let's do a couple of more problems from Math 209 from Concordia University. Okay. So, let's do problem 63. So that's problem 63. And the problem here is the following. So that y is equal with 1 over 1 plus ct, ce to the minus t is a solution to the differential equation dy over dt is equal with y over 1 minus y. For any real number, find a particular solution that passes through 0 point minus 1. So, there are two ways of doing this. But let's start with the easiest way, which is to prove that this here, it's a solution of this by finding the derivative of this here. Okay, so which is the easiest thing. So let's find what is the derivative of this. So the derivative of y is y prime is equal with, okay, so this here you can write it as 1 plus ce to the minus t to the minus 1. So that means if you take the, the rule that the derivative of x to the n is n times x to the n minus 1, you can say that the derivative of this is minus 1 times the derivative times this. in the -2, and just to help you understand, this here we can rewrite it. This here we can rewrite it as 1 plus c e to the minus t to the -1. So now if you take the derivative of this, it will be -1 times this in the -2 times, using the chain rule, the derivative of what you have inside, which will be equal with, times. So c, and the derivative of 1 is 0, the derivative of this is c, and the derivative of e to the t to the minus t is c to the minus t. And again, because you use once more the chain rule, you have to put, because of this minus here, you have to put a minus here. So that will give you minus with minus is plus. This should be 1 plus c e to the minus t to the -2 times c e to the minus t. Okay, so now how this is, let's see now how this here is equal with this. This here is, come on, you see, this here is y times 1 minus y. Sorry about that. I mean, if you take dy over dx, that should be equal with y, which is this here, times 1 minus y, which is this here. So now if you do here the calculations, you bring this up here with the minus, the one with the 1 goes away. So all of this becomes c e to the minus t in the numerator, and then you have this into the denominator times the same thing, so that becomes 1 plus c e to the minus t squared, which of course is exactly the same with this here. Sorry about that. I miscopy the problem. So now, so this is the general solution, this here. So, and of course, we have to find a particular solution for, if we know that the graph of this solution passes from 0 point -1, that should not be any problem. So, I mean, if we know that this is the solution, you just put whatever x0 and y -1, and that should give you -1 is equal with 1 over 1, and this here will become e to the 0 is 1, this will become plus c. Okay, so that means that 1 plus c minus 1, sorry, -1 minus c -1 minus c is equal with 1. So that means that c is equal with -2. So that means that just go here and you substitute whatever c -2, and that will give you the particular solution, which is 1 plus 2, -2, set e in the minus t. So this here is the particular solution, and this here is the general solution. Now, let's do a couple of more problems, and I think that's about it. So, yeah, I mean, this is really pretty simple one. And this has to do with what we said before about growth and decay. So, that's a little application in again in commerce. That's problem 77. So, has to do with continuous compound interest. Yeah, I mean, it's really a very simple program. It's find the amount A in an account after T years if dA over dt is equal with 0.03 A, and we have also that when we start A at 0 is equal with 1000. In here, if you remember what we did with growth, either you take it directly or you can just solve it again. Me, I prefer to solve it again. So if you bring here the A, you have dA over A is equal with 0.03 t. So we take now the integral in, so here this is dt. Take the integral in both sides, so you have that ln of A is equal with 0.03 t plus c. And now that means that A, according again with the definition of the logarithmic function, you have that A is equal with e to the 0.03 t plus c. And now if you apply the initial condition, we know that t is equal with 0, the A is 1000, so that means that 1000 is equal with e to the c. Okay, so and now because we can write this here, the A is equal with e to the 0.03 t plus c, you can write it as A is equal with e to the 0.03 t times e to the c, and since e to the c is equal to 1000, you get finally that A is equal to 1000 times e to the 0.03 t, which of course is a case of exponential growth. Now, let's do a couple of more problems. Okay. Okay, I will do the last problem, which is problem number 81. It's always from the book that you use at Concordia University, or Math 209. And we're always on the section differential equations, growth and decay. Okay, so this is problem 81, and it has to do with price demand. So we have that the marginal price dP over dx at x units of demand per week is proportional to the price P. Okay, so I mean, how can we write this? And since it's proportional, that's how we should write it. So there is no weekly demand at price $100 per unit. So that means that at P at 0 is equal with 100. Okay, let me repeat again. There is no weekly demand at a price of $100 per unit. So that means there is zero demand, so the x is 0 when the price is 100. And there is a weekly demand of 5. So that means when x is equal with 5, there is a weekly demand of 5 units at the price of 77.88. This is always dollars, Canadians, or American, or whatever. So, okay. So, first question is to find the price demand equation. Okay, that's not a big deal. So, again, the same story. So what do we, I mean, we already did this before. So, you know, as a problem and as a theory. So we already know that P, it should be equal with, let's say, P0, like the, let me do it, solve it again. So, I mean, what do we have here? We have dP over P is equal with K dx. And I mean, again, you know, if you take the integral here, you have the ln of P is equal with K x plus C. And from that, you have that P is equal with e to the k x plus c. And we know that x is equal with 0. We have that p is equal with 100, so that means that 100 is equal, you know, e to the c. So that means that we can rewrite this here as P is equal with 100 times e to the x, excuse me, e to the kx, sorry. Okay, so yeah, okay, and now I mean, what we're missing from the price demand equation is the k. Okay, we have to find how much this k is, so that's why they give us one more equation here. So we know now that at x is equal with 5, p is equal with 77.88. So that means that we put here 77.88 is equal with 100 times e to the, I mean, we know that x now is equal with 5, so e to the 5k, okay, x is equal with 5. And now if you want to find how much k is, just have to apply the ln function in both sides of the equation. I mean, before we do this, we can divide both sides by 100. So that means that the ln of 77.88 over 100 is equal with ln of this, which is 5k. So that means that if you divide now both sides with 5, that should be your k. I mean, you can calculate that with your calculator. I don't think so that's a problem. So that means that we know how much is the k. So so that will give you the price demand equation. I mean, the second question is now if you have your k, they ask you to find the demand at 10 units per week. So that's pretty easy. If you have the equation, you just put whatever x equal with 10, and that will give you the price demand equation. So that will give you the price. Okay, if you substitute here x equal with 10, that will give you the price. And finally, the last question is to graph the price demand equation. So the price demand equation. So the only thing we have to calculate is if if you do this calculation here, I don't have a calculator now handy in front of me, but if you do this calculation, because whatever you have here is less than 1, I mean 77.88 over 100 is less than 1, so that means that the ln of this is negative. So and then divided also by 5, it's negative. So that means that this k here, it's a negative number. I mean, which is the only thing that it matters. And so that means that since it's negative, we have a decay. So if you want to graph it roughly, the graph of this, it would be a decay, which is approximately, and here is the Here is the price in dollars, and here is the time X in weeks. So, and we know that it starts, the initial value, it's 100. So let's say approximately here it's 100. So that should go something like this. You know, we have done this before. So that's about this live session of Math 209 from Concordia University again, which has to do with the topic of differential equations, growth and decay. So thank you for taking the time to view this live presentation, and many more will come, and I hope you join us soon. I will post the times and dates that I will have my next live presentation. So bye for now.